So, inclusion exclusion principle. So, inclusion exclusion formula if you like. So, recall. So, this is from your first chapter. We said that probability of A I is equal to sum over I equals 1 through n probability of A I minus sum over I less than j probability of section A j dot 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 minus. So, plus minus 1 to the n minus 1 probability of intersection. So, this is the inclusion exclusion rule, right. Just recall this from memory, right. So, you have to add all the probabilities, subtract the probabilities of intersections 2 at a time, add 3 at a time, subtract 4 at a time and so on, right. So, in order to prove this, so I am going to prove this, okay, and I am going to finish it here. Okay. This is all the space we will take. Okay. So, you will agree with me that indicator of this set. So, I am looking at the indicator of that event. Okay. So, this is the indication, this is the indicator of that at least one of the A i's occurs, one of the A 1 through A n occurs, and that is equal to 1 minus the indicator that all the A i's fail to occur, correct. So, this is the indicator that all the A i's fail to occur. 1 minus the indicator of that is the indicator of at least one A I occurring, right. This you will agree, right. Now, what is the indicator of, so what is the indicator of A intersection B? The indicator of A times indicator of B, correct. Indicator of A intersection B is indicator of A times indicator of B. So, this can be written as 1 minus the indicator of, well actually let me write this as product indicator A I complement I equals 1 through n, right. Now, indicator of A I complement is 1 minus indicator of A I, right. So, I am going to write this as 1 minus product one minus indicator A I, agreed with me so far. Now, one more step is all that is needed. So, you have to go from indicator to probability. How do you do that? So, how do you go from the indicator of event to the probability of event? Take expectations, right, because indicator of I of A is equal to probability of A, correct. So, you take indicator of this, what happens? You get this, correct, and then you have to take expectation here, right. So, what will happen here? So, if you expand this out, so the 1 will there are a bunch of 1 minus terms here, right. So, the 1 will hit with this the first one here. So, if you expand this product out, what you will get is you will get a sum of the indicators, right, minus you will get indicator A I, indicator A j, right, all the I j's. You will essentially get terms like this. You take expectations, you will get this. Okay. So, you expand and take expectations, that is it, you are done. Expand out and take expectations. right, and you will be done. Okay. So, in order to write it, maybe it will take a little more space, but I am sure you can do that, right. So, you just expand this product out. This is like 1 minus these indicators, this will be 1 minus IA 1 minus IA 2, so on, and then there will be 2 terms 2 at a time, 3 at a time, and so on. Finally, there will be a product of minus 1 to the n minus 1 indicator of all the product of the indicators of all the AIs, which will finally give you that term. Finally, if you take expectation, you get that term. Okay. So, this is a very simple proof of inclusion exclusion principle. Okay. Actually, this is the most transparent way to see why this inclusion exclusion principle is even true, right. The induction proof, while it is a mathematically correct proof, it gives you does not give you much more intuition about what is going on, right. This gives you a very structural intuition on why this inclusion exclusion principle is true. Are there any questions? If there are no more questions, we will start discussing monotone convergence theorem. Okay. Maybe I will not finish discussing today, but we will start off discussing what it is about. Okay. So, this monotone convergence theorem, as I said, is probably the most important theorem in all of integration theory, all right. So, the monotone convergence theorem qualitatively what does it do? It just gives you a way, gives you conditions, a condition rather, under which you can interchange limit and integral. Okay. So, normally if you have limit n tending to infinity integral f n, you have a sequence of functions f n. Okay. Let us say you have integral f n d mu, right, or you can think of it as integral f n dx if you like. If you just want to think of integrating on the real line, you probably know that you cannot always integrate interchange in limit and integration, right. So, the limit of an integral is not always equal to the integral of a limit. We will see some examples. Okay. But the monotone convergence theorem says, gives one sufficient condition under which you can interchange limit and integration. Okay. Namely, you can say that the limit of the integral is same as the integral of the limit function. So, in particular, if f n converges to some function f, integral of f n need not always be equal to integral of f. Okay. In particular, the monotone convergence theorem says, if f n converges to f in a monotone way, right. Suppose f n monotonically increases and converges to f, or f n monotonically decreases and converges to some f, then you can interchange limit and integration. Okay. So, in that case you will in fact have that integral limit of the integral is equal to the integral of the limit. Okay. So, that is what the monotone convergence theorem says. Okay. It is actually to state it is fairly simple. Okay. But before I state this properly, I want to define some concepts on convergence of functions. Okay. Let f n from omega to r this could actually be R union plus or minus infinity as well. Okay. B a sequence of measurable functions. Definition: we say Fn converges to f. F is another function from omega to r, okay, r the real line. We say Fn converges to f pointwise if for all omega in omega Fn of omega converges to f of omega. Okay. So, pointwise convergence of function is a this is what this is it means, right. You fix an omega in the sample space in your set omega, and for every omega Fn of omega will be a sequence of what? Fix an omega, Fn of omega is a sequence of real numbers, well not including plus minus infinity, not quite real numbers. So, this is a sequence, let us just say it is a sequence of real numbers. If it is true that that sequence of real numbers converges to this real number f of omega, and if this holds for every omega in omega, then we say Fn converges to f pointwise. Okay. This is clear. So, these Fn's, so this could be a sample space, this could be random variables for example. Okay. Fn's could be xn's, some random variables, and in that case you say that random variables xn converges pointwise to x if for every omega in the sample space xn of omega converges to x of omega for example. Okay. Now, it remains to be well, the one little thing that I have not really spoken about is that if you have a sequence of functions converging pointwise, the limit function is also a measurable function. Whenever these Fn's are measurable, the limit function is always a measurable function. Okay. This is something that can be proven. Okay. I have not done it in class, but it is always the case that if you have a sequence of measurable functions converging pointwise, then the limit is always a measurable function. Okay. This can be proven. So, is the definition clear? And then I will just put one more definition which is closely allied. Let us say that, so omega, let me say that omega f mu is my measure space. Okay. So, omega is this guy and I have f and mu on that space as well. We say that f n converges to f mu almost everywhere if, what do you suspect it is? What do you think this will mean? This convergence holds not necessarily for every omega in the sample space, but instead it may fail to hold on a set of mu measure 0. Okay. If f n of omega converges to f of omega for all omega except perhaps on a set of mu measure 0. Okay, this is also a definition. So, this is slightly weaker definition than this. Okay. This is saying that for every omega in omega you need this convergence f n of omega converging to f of omega. Here you relax saying, oh maybe it is not always true that, so it is not true that for every omega it holds. There may be a few omegas or a countable set of omegas or some mu measured 0 set of omegas, right, some small set, right, some there were 0 measure set where the measure is mu, right. On that set you do not have convergence or you may not have convergence, right, you can't quite say what f n of omega is doing on a 0 measure set, but outside that 0 measure set you have convergence. In other words, there is a set A, a subset A of omega which has full mu measure where convergence happens. Okay. So, in the context of probabilities, this has a very important interpretation which we will come to a little bit later again. So, this will become almost sure convergence of random variables. Have you heard that term before? Almost sure convergence of random variables. So, there we have a sequence of random variables x n, you have x n of omega converging to x of omega, not necessarily for all omega in the sample space, but on a set of probability 1, right. There may be 0 probability omegas where the convergence does not happen. Okay. So, this is almost sure convergence when you are talking about convergence of random variables. Okay. I will write that down explicitly a little bit later when we study convergence of random variables. Okay. Okay, so far okay, the definitions everybody fine. See now, so here, so this is pointwise convergence, right. Now the issue is if you have a measurable function converging pointwise to f of omega is always measurable. Now the question is if you integrate f n d mu, right, if you integrate f n d mu you get some sequence of numbers, right, integral f 1 d mu will be some number, integral f 2 d mu will be some number. So, integrating f n d mu gives you a sequence of real numbers, right. Now the question is does that sequence converge at all, right, that is question number 1. If it does converge, does it converge to the integral of f d mu? Okay, that is the question we are trying to address. Okay. The answer is no, generally that is not true. Even if you have convergence of f for every omega in omega, it is not true that integral f 1 d mu is equal to integral f d mu, not true. Okay. So, the question we are trying to answer is this: can we interchange limit and integration? See, that is the colloquial question, right, i.e., if let us say f n of omega converges to f of omega pointwise, is it true that integral f n d mu converges to integral f d mu? Okay. Answer is no. Okay. So, what I am saying is, so rather so in another way of writing is, if you want to write it more explicitly, is it true that the limit of the integral is equal to integral of the limit function? Okay, if this is a little more explicit you can take this. Okay. It is not true that this is not true. Okay. To see an example, I will just conclude with an example. let us say you take, let my omega f p be my favorite 0 1 integral 0 1 interval endowed with Borel and Lebesgue measure. Okay. That is my probability space. I want to define f n of omega is equal to n for 0 less than or equal to 0 less than or equal to omega less than or equal to 1 over n, okay, or less than 1 over n, okay, and 0 otherwise. Okay. So, that is my sequence of functions. So, f n of omega will look like that. So, if I plot it, so everything is in, all the action is in 0 1 interval. Okay, this is 0 1 interval. So, f 1 will be 1 in 0 to 1, f 2 will be 2 in 0 to half, f n will be n. So, this will be 1 over n, solid dot here, 0 everywhere here, hollow dot here, right, solid dot here. Actually, it does not matter what the, here it is a hollow dot, here it is a solid dot. The functional value is n. Okay. Here you will see that, so if you want to, so integral, what is integral f n d lambda? So, I am going to integrate f n with Lebesgue measure. Okay. Integral f n d lambda will be equal to 1, for all n this is equal to 1. On the other hand, if you look at the limit function, so the limit function f n will be, so for all omega lying, so for all omega that is strictly bigger than 0, the limit function will be 0, correct. At 0 the function will be plus infinity, actually because I have put a less than or equal to here. Actually, if I put a, so if I put a strictly less than here, the limit function will in fact be 0 everywhere, right. But yeah, I mean, so if you like, so to avoid confusion, let us just take this. Okay. So, let me just put the function at 0 here, okay, just avoiding confusion. So, let me do that, and at 0 it is 0, the function is 0. So, the limit function is equal to 0 for all omega and omega, correct, because you give me, no matter which omega you give me, there will be some n beyond which the function is 0, right. So, the limit function is identically 0, correct. So, if I look at f defined as limit f n, this is 0 for all omega, and integral f d mu will be equal to what, 0, right, and this is not equal to 1, right. So, integral f n d lambda is equal to 1. So, this implies limit n tending to infinity integral f n d lambda is also equal to 1, right. So, this integral is always 1. So, the limit is 1, the limit of the integral is 1, but the integral of the limit is 0. Okay. So, it is clearly not the case that you can blindly interchange limit and integration. Very simple example says that you cannot do it, right. So, I made this strictly lesser. So, even if this was less than or equal to, the limit function will be 0 for all positive omega, and it will take the value plus infinity at only at 0, okay. And because it is a function that is 0 almost everywhere, integral of a function which is 0 almost everywhere is 0. So, it would not have mattered even if I had less than or equal to here, there will just be one point where the function is plus infinity, but that one point has measured 0. So, there is no difference, okay. Is that clear? So, you cannot interchange limit and integration. So, what we will see next is next class I will state the monotone convergence theorem, which says that if this limit were to be a monotone limit, if f n converges to f monotonically, then it is always the case that you can interchange limit and integration. So, in this case monotonicity does not hold, right, because f n will look like this and f n plus 1 will look like that, right. So, it is not true that they are monotone in n, right. So, we will see this next class.